We shall make use of the second fundamental theorem of calculus, which we learned in the last week's lectures, to actually compute integrals. We cannot be just telling you, okay, do this, do that, and this is it will happen with abstract quantities or functions. We need to also tell you how to go ahead and actually make a exact calculation, because that is what you really need. So, if capital F is a function such that which is differentiable and its derivative is equal to f of x, then we say that the indefinite integral f of x dx is nothing but f of x plus a constant. So, what we are now doing, it is called integration in elementary terms. Actually, it means that for simple situations like this, you can actually do some integration. But for example, if I look at a function like this, e to the power minus x square dx, this cannot be integrated in this form, because you cannot find a capital F which is differentiable for which f dash x would be exactly equal to e to the power minus x square. So, for those cases where it is possible, we say that indefinite integration is possible, and then we can actually write down the real stuff. So, of course, if the function f is continuous, you already know that you will have, if you can, you can always have set these sort of primitives. It can be always done, but for a continuous function, if you can actually find a function a to x the way we did the mean value theorem, then of course you know that that thing actually works, that capital F works. Basically, if you actually can figure out this, that f is a continuous function and then f is differential, then if this is this, let us say it is f t dt. So, then see, sometimes people might ask why I am not writing t here, because I have taken x here. So, these are all dummy variables, even if you write x does not matter once you understand the situation. So, then of course, you can do all this elementary stuff, but it is not so often that it is not that for everything that you have, any damn function, continuous function you are able to write, anything that you are able to write, you will just always get a elementary function, for which you will always get a capital F, for which f dash x would be that function. So, here is one example, but by the way, when we will learn improper integral, this integral with certain limits, a minus infinity to plus infinity, becomes an important integral. So, for example, if I have a thing like this makes huge sense. This answer would be root pi if I have not forgotten it. So, this makes huge sense, has applications in statistics, the normal distribution, and the interesting part is that when you just take off these two things, this makes no sense. And these are the things that you have to keep in mind while doing your math. And so, let us start with very simple things, for example, log x. So, for example, if you differentiate a log of x, so you take the ddx of log x, so what do you get? You get 1 by x. Of course, you know that you have your function x cannot be chosen to be 0. Of course, you know that x cannot be chosen to be negative either, even though 1 by x makes sense if x is negative, but log of x would never make sense. So, then you write the integral of 1 by x dx is log of x plus c. In fact, this thing leads to what is called the logarithmic function. Sometimes log, in a modern way, you can think that log can be calculated in this format. So, So, if you are given x and a log x and you simply numerically evaluate this integral, there is some techniques by which you can evaluate integrals. We will show them as one of the applications and how to evaluate integrals. So, they will come as one of the week's lectures here, that how to evaluate integrals, and then we will apply those stuff. So, what I want to tell you is that once you do that, you would realize that you can actually compute log x by computing this integral. So, though logarithms were known much before calculus, but you can actually use this very simple idea of the fundamental theorem of calculus to actually compute log x. So, this is sometimes called the logarithmic function. One of the greatest thing that happens is the use of the integration by parts. So, I have already taught you what is integration by parts when we are doing definite integrals, but if I just write down what is integration by parts, in this case, in the standard case, it will be like this. So, you just do not have to put the limits, the a b limits, that is it, and the same story would go on. Now, here you would have, so I am integrating f of x and gx, so dx. So, what you do, you keep the first function fixed, say integrate the second, integrate the second function minus integrate, first you take the ddx of the first function fx, and then integrate gx dx. So, this whole thing with another dx. So, there are two dx's here, basically you integrate this, then you integrate that. But when you integrate this thing inside, you do not write the constant, because the constant will finally get absorbed in the constant at the end. So, that is what you do. It's here you do not put the limits, you see, you do not have the limits anymore. So, that is what it is. For example, if I take an arbitrary function, if I remember my own younger undergrad days or so, I think I learned this in high school, but so say e to the power x, x square dx. So, let us see. It is not so easy to immediately say, okay, one can say, okay, I will put x square is t, x is, then you will have 2x, so e to the power t, but it will again be the same situation. The substitution is the substitution method of integration that you learn at high school will just not work here so easily. So, what you really have to do is to think about it in terms of integration by parts, because you can integrate terms. So, keep the first function there, if you integrate this, it will become x cube by 3. Do not put the constant in, because the constant finally is a part of the whole thing that you can just add at the end. So, minus integration, the ddx is again e to the power x and x cube by 3 dx. So, this is what is happening. So, you can say, okay, I am stuck with a similar situation. So, you keep on applying, so this will keep on increasing. So, this sort of integral, so what is happening is that you can have some relations between them, and then you can collate to get some better one. For example, maybe I will try something else, I will take a more simple example. Maybe I will take instead of x square, because so you have come to x cube. So, you might think, oh, I made a mistake, it is increasing. So, if I again try integration by parts, I will have another x4. So, how will I go? So, here there is this, so you have chosen this as the first function. So, this was your f and this was your g. So, when you face such situations where your powers are increasing and things are just getting out of control, you can try to switch the f and g mode. So, you switch this mode and you rewrite this integral as, integration by parts is one of the most important tools. You rewrite this integral as 1 by as your x square into e to the power x dx, right. So, this now becomes f and this now becomes g, and that would give you, let me call this as the integral I. So, this will give you x square e to the power x minus, now if I take the derivative of my power of x goes down, x e to the power x sorry 2x. So, what is happening is my power has now gone down. So, that is a question for jubilation. Of course, I am not putting the c, you can put the c at the end, minus 2 of, now I now go back to this, consider this x as f and this as g, again I reapply the integration by parts, which will give me just as this x e to the power x minus integral, now if I take the derivative of x it will become 1, so e to the power x dx. So, now if I rewrite this, so what I am having x square e to the power x minus 2 of x ex minus ex plus c. So, ex plus c is whatever, the c will go out plus some c. So, basically because now you have the integration by parts formula. So, if you want to write it down somewhere, let me write it down, integral f g dx. I am just writing in code, not writing f x g x, you can understand. So, f into integral g dx minus f dash x into integral g dx. So, this is the formula. Here g dx into dx. So, this is the formula which we just wrote down and brought it here. So, we are doing the same thing here basically. So, here you will have x square e to the power x minus 2x ex plus 2 e to the power x plus c. So, how do you check that this is true? You take the derivative of this and check that it will give you back x square ex. So, now you can actually develop what are called recursive relations here. Basically, if I define I n as integral x to the power n e to the power x dx, then how you can have a relation between I n and its next one, I n minus 1 possibly here, because you can again switch this whole thing to have x n e to the power x minus integral n x n minus 1 e to the power x dx. So, I can write this as x n, if I call this as I n and the power is n, then this is nothing but integral I n minus 1. So, here is a recursive relation. So, basically when I is 2, here it is I 2 basically, this was I 2 essentially if you go by this notation. So, I 2 is nothing but x square ex minus 2 into I 1. So, that is the relation. So, these integration by parts make certain relations between certain typical type of integrals. So, you could have for example, so suppose now I ask you to do this integral, it is a very typical and a famous example. So, integral of log x dx, log x essentially we are meaning that log to base e, in calculus that is what is the meaning, base 10 does not matter, but base 10 we do not really want to work with because that has, you know, you can do a lot of things when you have that exponential as the base. So, log x dx. So, how will you do this log x dx business? How do you know which function is your derivative stuff? So, here you are going to have to invent something. Here you are going to write log x as, and how do you, it is not so apparent to write a function whose derivative is log x. What you are going to do is you are going to write log x into 1. So, this is your f and g is a constant function which is gx equal to 1 for all the x, and then you see, you apply the integration by parts and you see the power of this whole technique. Then what you do is just like here you keep the log x fixed. So, log x, and if you integrate this is x. So, x log x minus integral d dx of log x, which is 1 by x into x dx. So, x gets cancelled. So, it is x log x minus x. So, surprisingly not so simple looking integrals can have a very simple solution once you have these kind of stuff. So, I do not want to get into more of these issues. I would rather concentrate on showing you some other examples. So, I have just halted the camera for a while and just wanted to write down these integrals, integrals of trigonometric functions, because it is asking sin x to the power n, cos x to the power n, you are integrating, you want to find the indefinite integral or you want to find the capital F. These formulas become very handy to evolve. I would like you to, when you practice some integration, to do some of these trigonometric integrals. So, I will not get into too much detail. So, what I will do is I will take a problem from Spivak, an example, and show you that how this integral can be handled with these formulas. So, first we will take an even power of sine and then we can take an odd power of sine and then we can we can apply sort of other techniques. So, here so for example, so integral, that is the example which Spivak uses, is this one. So, what we will do is write it as integral sine square x whole square dx. So, here I know what is sine square x, it is 1 minus cos 2x by 2. So, it is 1 minus cos 2x by 2 whole square dx. Now, you just have to open the bracket, expand the sum. So, it is 1/4 into 1 minus 2 cos x plus cos square x dx. So, then of course, it becomes very simple, 1/4 d, sorry, thank you, cos 2x, cos square 2x. So, this is just 1/4 of dx minus integral 2 of cos 2x dx. You know what cos 2x dx is. You see, when now you have this additional 2 by 4, so it will become half here, and 1/4 of this part cos square 2x. Now, what is this cos square 2x? How will you handle this situation? So, here you put 2x, here you put 2x, it will become 4x. So, basically if you take the integral out, so you can just you just really have to compute this integral. This is what you will know what the integral is. This is minus sine of 2x by 2, 1/2 of sine minus sine 2x. So, you know these integral, this is this is the elementary thing. For here again you have to use this formula. You see, in the same formula we are making use of both of these formulas. So, cos square 2x dx can be again written as integral 1 plus cos 4x by 2 whole square. So, I have reduced again the integration. Now, the power has reduced from the power square of square, it has now come to just the square, and so you can write down this again in sorry, thank you. So, from power of power, so square of square, it has come down to just the square here. So, here I just need this, not square, thank you. So, I will just use the simple thing. Now, it will become half of dx plus half of integral cos 4x dx, and I am not going to write these formulas for you, these are standard high school stuff which you can write. So, I would really So you can ask, okay, this is even, but if it is odd, so if you have sine say what 5x dx, what am I supposed to do? So what I am the only thing I am supposed to do is to write it as sin x sin 4x dx, and then integrate. Now then, so for this part you know the integration, right. So for this part you already know the integration sin 4x. So now you go by the integration by parts. So you can look into formulas like sin n to the power x dx, sorry, n to the power x cos m x dx. You should try this at home. These are some good exercises, but I am sure it is not a good exercise for old man like me at the board at this hour. So I would rather leave these things to you. Now you can actually say for sin nx, instead of taking these sort of roots, here we have used the formula and taken some roots, taken one approach. We can use directly integration by parts. If I am faced with this problem, I will always use integration by parts. So I am trying to tell you how powerful integration by parts it would be, which is I think the central jewel of these elementary calculation approaches. Sorry. So here you can actually do sin n into sin n minus 1, it does not matter, sin n x into sin x into sin x to the power n minus 1 dx, and then just do on. Keep this for your second, make this as a first function and then take the derivative of this and then just go ahead. So basically you will simply have here, so take this as f and this is g. So you will have sin x of n minus 1 into cos x minus integral. Now you take the derivative of this, it will become n minus 1. So it will become n minus 1 into sin x sin x n minus 1 minus 1 n minus 2 into cos x into derivative of sin is cos x, and you already have cos x from here, this integration minus. So here I will have cos x into minus cos x, which is coming from here. So it will become cos x square, and outside that will come and become plus. So cos sin x cos square x, I mean cos x whole square into dx. So that is where what the formula looks like. So what would happen? I can just now write integral sin nx dx is equal to minus sin x. So this is my integral in. So in is equal to this one, this integral. So it is sin x n minus 1 cos x plus n minus 1 sin x integral sin x n minus 2, and cos square x can be written as 1 minus sin square x, and then that will give you the recursive relation. So these recursive relations become very important in elementary calculation. In the days when people were calculating things by hands, these were actually your feedback systems. So xn is f of xn plus 1, these are algorithms. Or in those days, while people did integration, they had actually invented the way we now do algorithms. So you have a function f where you put xn, you get xn plus 1, and you can put xn plus 1 here, you will get xn plus 2. that sort of feedback system. So, that is exactly the feedback mechanism that you are getting here. So, that is finally minus sine of x n minus 1 cos x plus n minus 1 integral sine of x n minus 2 dx, right, plus minus n minus 1 integral, if I multiply this, it will become sine n of x dx, right. This is, so what I am getting, so this is I n is equal to minus sine x n minus 1 cosine x plus n minus 1 into I n minus 2 minus n minus 1 into I n. So, you take it to the other side. So, what we will have I n, so I n into I n plus n minus 1 into I n. So, you will have n I n, right. So, then you divide by n. So, it will become minus 1 by n sine x n minus 1 cosine x plus n 1 minus 1 by n, this is n minus 1 by n, right, into I n minus 2. So, that is the recursive formula. So, now you can find, so if you want to try I 4, if you what we are thinking, so just put 4 here, that is it. So, you do not have to do all these things. So, now the last part is about partial fractions, which is a very important class of stuff, and I would again do it from Spivak. Here some 1 or 2 good examples. There are some results, mathematical results, but I know nowadays people might not be too much interested in going into details of things, but so they are looking at functions in this way. So, you are going to integrate what are called rational functions. So, a rational function is a function R x which is represented as the ratio of two polynomial functions. So, and then we are looking at what is, we are asking the question how to integrate this, where q x is of course not equal to 0 and both are polynomials of certain degree. So, q x cannot be 0. So, both are, so these are polynomials of some degree. So, that is a standard example that is given in many books, but this is one of the most important class of functions. So, what people do is given a class, there is a technique of writing it. So, if we go into the technique of writing it, it will become terrifically complex. The idea is that you have the polynomial q x and then you factorize the polynomial. So, suppose I have been able to write p x in q x into h x into g x, right. So, you now want to do a very simple calculation. Now, you want to write p x h x g x as a of h x plus b of g x, and you want to figure out what is this a and b essentially. It depends, sorry, these are all functions of x, sorry, I made a mistake, that has to be functions of x. So, you want to find out what is this a x and b x. So, basically you are writing the last part as a function. So, basically what is happening, g x into a x plus h x into b x is actually your p x. So, p x is essentially this polynomial is a x into g x plus b x into h x. So, we have to figure out this. How can one do that? So, this is an example. So, these examples we do not have really time to really compute out the examples here, but this is an important class. So, some examples will be given, will be handed out in the notes. I know there is a demand of notes in the forum. I will start sending 1 or 2 papers already, 1 or 2 chapters, but these sort of things where we are not in the class, I would request my TS to take some examples of these rational functions and actually write them up, scan them and put them on the notice board. So, these examples, everything cannot be done in the class, because actually if you want to break certain things, it will take a huge long time, which is not feasible, because we are already exceeding our class timings. Quite frequently we are doing so. So, we have some idea now. Specifically, I wanted to show you the power of doing this whole calculating indefinite integrals. The key idea was to show you how powerful the integration by parts method is. In advanced mathematics, many things which require integration by parts come into the foray. So, this is a very manipulative thing here. Really, we are not going to look into the much of mathematical understanding. Of course, there is a particular way you can write this whole thing into, and then you can write down this integration in certain way, but I will ask the my TS to put in up some examples of these. Just they will scan 2-3 examples, so you can see those examples. Thank you very much.